So if I give you a set of integers or whole numbers or natural numbers or whatever it might be, one of the questions I may ask you to be able to do is to be able to express that set in terms of all the other sets. So we define U to be the universe, which is the integers. A is the whole numbers, which is certainly a subset of integers. B is the natural numbers. C is the odd integers. D is the even integers. And just to remind you, the whole numbers, which we defined as set A, is the set 0, 1, 2, 3, 4, etc. However, the natural numbers, which we define to be set B, the only difference between whole and natural is that natural starts at 1 instead of 0. So, and then certainly we understand what odd integers are and even integers. Divisible by 2 for even has the form 2n plus 1 for odd. So let's take a look and be able to answer some of these or be able to perform some of these operations in terms of the others. So we have odd integers set difference to even integers. And remember what a set difference is. Set difference basically takes all the elements that are in set D in this case, and any overlap, we eliminate that. But remember that odd and even integers are disjoint sets. So in this case, the answer would just be C, and the reason being is because there are no elements shared between C and D. So that makes it really easy. Now, intersection. Remember, intersection basically says all the elements that are in both of the sets. So we just defined whole and natural numbers. So if we look at A and we look at B, if we go through and express that, then what that essentially means is that we're just intersecting 1, 2, 3, 4, etc. All right, but 1, 2, 3, 4 is exactly set B. All right, so the only difference between those two sets is going to be set A contains 0, set B does not. A union B. Basically, we're going to juxtapose A and B together. If we juxtapose them together, again, the only element that's different is this 0. So if we kind of blend A and B together into one set, we're going to have 0, 1, 2, 3, 4, and that's exactly set A. Finally, U minus A. U minus A is going to be the universe, which is all integers, minus the whole numbers. So remember, whole numbers are 0, 1, 2, 3, 4. So that basically means all I'm left with is the negative integers. So a way we could express that is U superscript negative. So now that we know how to do all these set operations with elements, set difference, intersection, union, complements, now we can move on to be able to prove some of the most axiomatic or some of the most fundamental definitions with respect to sets. To be able to do this, what we're going to need is we're going to need a few things. So first, we're going to need the basic logical equivalencies. And if you remember that paper, that's the one with De Morgan's law, those sorts of things, like the complement law, the idempotent, all those laws. Okay, so bring that back up. That's what we used on the first examination. All right. The other thing that we're going to need is these procedural definitions. And the procedural definitions are as follows. So, X is an element of A union B if X is an element of A or X is an element of B. X is an element of A intersect B if X is an element of A and X is an element of B. For set difference, X is an element of A minus B when X is an element of A and X is not an element of B. And then finally, X is an element of A complement when X is not an element of A. All right, so these are going to be 4 of the most fundamental procedural definitions that we need to know to be able to do any sort of proofs with respect to, or any proofs with respect to basic sets. So finally, to prove that the two sets are equal, that is set A equals B, first we're going to have to show that A is a subset of B, okay, and what that means is that for all x in A is contained, or all x in B, excuse me, is contained in A. And then we'll also have to show the converse of that. We'll have to show that all x in A is contained in B. Right? So, other way around, excuse me. All right, so subset, A is a subset of B if all x in A is contained in B, and then all elements in B are contained in A. So in the next series of videos, we're going to take a look at how to do this. And unfortunately, it's a very taxing sort of process because we're going to have to utilize, when we do this, unfortunately, we're going to have to use division into cases. Because obviously there's two cases. Case 1 is going to be when we have to show A is a subset of B. Case 2 is going to be when B is a subset of A.